Welcome back to Empowering Introductory Algebra, the informative series created to assist students to build a strong basic algebra foundation leading to college-level studies. Hi, I'm Bob Young, Assistant Professor of Mathematics at Brevard Community College. With the help of the great support staff of WBCC, we continue to bring you introductory algebra lessons containing notes, graphics, tons of examples, and some study tips. Let's pick up where we left off in our last lesson. Now, in our last lesson, we were finishing formulas. So going to the graphic here, it says to solve a formula for a given variable, do the following. Identify the variable for which you want to isolate for or solve for. And that's usually pretty easy because they tell you that in the problem. And in step 2, multiply both sides of the equation to clear fractions or decimals if necessary. And we've discussed that with solving equations overall. And number 3, get all terms with the variable to be solved for on one side of the equation and all other terms on the other side. So going to the example I left off with last time before we ran out of time, we were solving the formula here, P equals AB over C. Now what does AB over C mean? It means A times B all divided by C. All right, and we're going to solve this formula for C, so the first thing we need to do is get rid of the fractions by undoing the division here. And to undo division, we have learned to multiply both sides of the equation to undo division. So if we multiply both sides by C, the C's will chop out over here or cross cancel, leaving us with PC, or P times C, equals A times B. Now, in order to solve for C, we want to go ahead and undo multiplication here. So to get rid of the P, we divide, to divide both sides by P. We want to get C by itself, so we're going to divide both sides by P, and that's going to give us C equals A times B all divided by P. Now, one thing I didn't mention in the last episode is we can check this. Now, we started out, let's go over here on the side with P equals AB over C. And we ended up solving for C over here. Okay, so what I want to do is go ahead and substitute some numbers in here and make this make sense. And we can substitute any numbers, because remember, variables are just simply numbers. So if we want to substitute some numbers in here and make this make sense, why don't we let A be the number 4, and we'll let B be the number 3, and then C will be the number 2. So we can actually check these formulas and make sure they make sense. So 4 times 3 multiplying would be 12 divided by 2. So substituting these numbers in for A, B, and C, P will come out to be 6 over here. All right. So in my finished formula over here, when I solve for C and I got C by itself, these numbers should also work in this solution as well. So let's see if they do. So we said that C was 2 over here, so we'll put 2 in for C, equals A times B is 4 times 3, all divided by P we said was 6, and looky here, we have 4 times 3 is 12 divided by 6 does give us 2, so we know our final formula here, which I kind of wrote through a little bit, does actually check and make sense. And the beautiful thing about algebra, you can put any numbers in the universe, any real numbers in here for A, B, C, and P, and they ought to make sense in your answer over here as well. All right, so you can check variable formulas by substituting in values. All right, the next example we want to talk about here on the bottom is A equals B plus C subtract D all divided by 5, and we want to solve this for B. All right, so again, to undo this fraction, to get rid of this divide 5 here, which is in our way, we're going to go ahead and multiply both sides of the equation by 5. And the 5s, you know what? Chop out. All right, so that leaves us with 5 times A equals B plus C subtract D. All right. So now if I want to go ahead and get B by itself, what has to go over here? Well, it doesn't take a rocket scientist to see that C's got to go and the D has got to go to get b by itself. So what undoes addition? We have learned this whole entire last few lessons that subtraction undoes addition. And whatever you do to one side of an equation, you must do to both sides. The BS rule still in effect. All right, subtract d to undo subtraction will add a d to both sides. And then, again, whatever we do to one, we do to both. So b will equal 5 times a, subtract c, plus d. So this is a really good example in what we've talked about in the last few lessons on equations, solving equations. To undo division, multiply. To undo addition, subtract. To undo subtraction, add. And whatever you do to one, do to both sides, and you will get a finished product down here. All right. So in review on finishing formulas, not only is this an important concept in math, but it will also be an important concept in your science classes as well. Your science teachers will love you if you get to that science book and you can take formulas and manipulate them and solve for different things, because a lot of times in the science books, that's exactly what happens. You have problems with formulas in them, and they give you certain things to solve for, and you have to actually use some algebra in order to, make that work. All right, so let's go ahead and go back to a graphic here next. The next thing we want to talk about is solving inequalities. All right, a little bit different than equations we've talked about. An inequality is a number sentence. It doesn't have the equals in it anymore. It's got the less than symbol, greater than, less than or equal to, greater than or equal to. And an example here, it says x is less than 5. Some numbers make the inequality true, while others do not. So for example on that, if you say x is less than 5, numbers like 4, 3, 2, 1, 0, -1, all the way back, all the negative numbers would work, when numbers like 6, 7, and 8 don't make sense in there. All right. So let's look at some examples over here with solving inequalities. And notice I've got the less than symbol versus the less than or equal to symbol. All right, and some folks have trouble even telling less than versus greater than apart. I remember in school when I taught back in junior high and middle school, I would say the less than, the alligator mouth always eats the larger number, or the arrow always points toward the smaller number. Or my wife's high school teacher even said, to remember less and greater, the less kind of looks like an L turned sideways. I don't know how well you see that, but I mean, whatever way you can remember it is good. All right, so let's play with a few of these concepts and see what we come up with. True or false examples. All right, so let's take -5 is less than -8. True or false? All right, now that one would be false. Because remember on our number line here, if we were going to make a number line, that -8 would be to the left of -5. And whatever's to the left is always smaller on a number line than whatever's to the right. All right, so you always want to remember that. Next example, -12 is greater than 0. Survey said, false. Not going to make sense either. All right, -6 less than or equal to 1. Well, any negative number is going to be less than any positive number. That equal sign now could be less than or equal to. So in this case, true. Okay. -10 less than or equal to -10. Well, no number is less than itself, but see with that equal connector in there, less than or equal to, it is equal to, so we can say that is true. All right, now had that just been -10 is less than -10 or greater than -10, we would have rung up the false. And with fractions, I know you guys love these things, and they throw negative fractions at you as well. Now remember the rule we used earlier when we had equal fractions. Let's say 2/4 equals 1/2. We said the cross products of equal fractions, when we cross multiplied, were always equal. Kind of holds with greater thans and inequalities too, less thans and so forth. If I take the negative on the 3 times 10, I get -30. So you always want to start with that top left-hand number and put it first. Okay, top left-hand number cross multiplying. And then we're going to have -7 times 4 is -28. All right, now Is this greater or less? Is negative 30 greater or less than negative 28 here? Well, it's to the left on the number line, negative 30. It would be less than. So for this case, since negative 30 is less than negative 28, this fraction, negative 3/4, would be less than negative 7/10. So this statement would be a resounding false here. All right, so that little cross product rule also will help you compare whether fractions, whether they be positive or negative, are greater than, less than, and so forth. So that's kind of a neat trick. All right, continuing some examples here. Let's go to another set. Let's talk about graphing inequalities. All right, we talked about numbers that made sense for x is less than 5 here. And in some textbooks, you'll see these little curly cues, which always mean set notation here. So sometimes you'll see this problem, which is really all we're after, written in this really fancy format here. So what this says is the set of all numbers x such that x is less than 5. All right, so on our number line, I think a key point to write here would be 5. And to show your instructor you have a good sense of number lineness here, we'll go ahead and put 6 over here and 4 to the left. You don't have to start from 0. I see some students want to start from 0 and fill up their number line. So we're just interested in the key numbers that graphing this is going to make sense for. Now, is 5 included if we're going to graph this inequality here? And I would say no, because, if you put 5 in for x here, 5 is not less than 5. We talked about that. So the graph is going to have an open circle on the 5, which shows it does not include the 5. And what we're going to do is we're going to shade all things on that number line to the left of 5, which is all numbers less than 5, including the arrow. All right, now why the arrow? Because we know numbers to the left of 5 go to 0 and all the negative numbers. Notice if I took a number on the right of the number line, like 7, and tried to substitute in here, it wouldn't make sense. 7 certainly is not less than 5. So if you want to look at it in that regard, all numbers over here to the right of 5 don't satisfy this inequality. All numbers here, yeah, they work. Happy region. Now, what if that was less than or equal to 5 versus just plain old less than? Well, the graph would look similar here. We would go ahead and put 5 on it and then some numbers around it. But with that equal to in there, instead of an open circle, we're going to put a closed circle, which means includes the number. And then we're just going to shade all the numbers to the left here. So I'm trying to use some colors here so you guys out there in the audience can see to shade there. And sometimes if you use highlighters, it really looks nice too. All right, so that's the difference between graphing with less than, open circle, does not include 5, versus less than or equal, does include 5. And let's go to the graphic here next. When we solve inequalities, a number that makes an inequality statement true is called a solution. The set of all solutions is called the solution set. And we saw in that previous examples, we had the little curly cues. When we have found the set of all solutions of an inequality, we say we have solved the inequality. And then we talked about this, but I wanted you to have it up here on the graphic, and my friend Michael does a great job with these graphics here. When graphing inequalities, an open circle on a number line shows the number is not part of the solution. When shaded, a closed circle indicates the number is part of the solution. So that's a major point that we've discussed. All right, so let's go back to some graphing problems again and some examples here. And we've got, in this case, y is greater than -3. Now notice I didn't use all the curly Q notations and all that. This is really the meat and potatoes of the problems here. So we're going to go ahead and put -3 on the number line. And to show the instructor we know our number line order, we're going to put -4 on that side and -2 to the right here. So we want to get this in correct order. And again, you don't have to go 0 all the way back. Now, open or closed circle on -3 doesn't have the equal to in it. We're going to put an open circle, and we're going to shade everything which way? Numbers greater than -3, it's kind of which way the inequality is pointing in this case. So that would be the graph of y all numbers greater than -3. This one's a special type of graphing inequality problem, and I've got a roommate at school here that we share an office, and he's from Tennessee. And he calls this a tweener problem. and Tennesseans, they call this a tweener problem. So what this says is x is between -2 and +3 on the number line. So we want to show in this graph all numbers between -2 and +3. So I'm going to go ahead and put -2 over here, and then I can go ahead and fill in some numbers, -1, 0, up until 3. All right, and notice the symbols here. I want to make sure I hammer this point across. Is -2 going to be part of this graph? Not with this symbol. See, so the -2 has this symbol on it, open circle, does not include -2. On the 3, closed circle, does include, less than or equal to 3. All right, and if x is between these numbers, we are going to shade all numbers in between. So this would be the solution set of this inequality statement, all these numbers between here. All right, so the shaded region is really what we're after on these. Okay, continuing. Graphing the inequalities. Here's another little thing that sometimes throws students off when it comes to inequalities, and that's the different ways you can write them. And let's see if this makes sense to y'all before we try to graph this next example. If A is less than B, well, then B must be greater than A. Now, if it doesn't make sense with variables, remember all variables are numbers. Put some numbers in here and see if we can make this make sense. How about if 1 is less than 5, if I put 1 in for A and 5 in for B, well, then we know that if we flip it around, then 5 had better be what? Greater than 1. All right? Because sometimes a student will get to one of these, they'll slip the variable on the right-hand side of the equation on these inequalities, and they'll say, oh, I've got that one. If you looked at the previous examples, they'll go ahead and put 7 here, 8, and 6 over here to the left, and they'll say, okay, that's an open circle on 7, and they'll say, okay, well, it's pointing that way, so I got to shade everything to the right, and then it's, oh no, don't go there. It's a bad dark place. All right, so if you put 8, if you try to shade 8 and you put it in here, does it make sense? 7 is greater than 8. So remember, if you don't like that variable on the right side, you can rewrite this using this little gem of a rule up here and just say, well, if 7's greater than x, if we're trying to show all numbers x there, well, then x would have to be less than 7. All right, so we'll go ahead and now shade the correct region there, which would be all numbers to the left. Okay, so all of these numbers make sense in either one of these. The ones to the right of 7 do not. Do not. All right, now we're going to actually solve some inequalities, and we're going to tie some things in to equations now. We're going to solve some inequalities and tie some things in. So it says solve the inequality for the given variable, then graph. So just like equations, we're going to say to undo addition, we're going to hit it with subtraction. So we're going to go ahead and subtract 9 from both sides of this inequality, and that'll leave us with x is less than or equal to 5 minus 9, different sign, subtract, sign of the larger number is negative. So if we were to graph this on the number line, we would put the -4 here in the middle, some numbers to the right and left of -4 to show the instructor we have a good number line sense. Open or close circle on -4. It's got the equal sign, folks, so we're going to go ahead and put the closed circle there and shade everything which direction? Everything to the left of -4. See, so it's kind of nice. When you've got that variable on the left side of inequalities, it's kind of like you just shade the direction it's pointed, but that variable has to be over here. All right, so I'm always going to, when I solve for these, try to get the letters on the left and the numbers on the right. And we were kind of doing that with equations anyway, so that's great. That's great. All right, next example. 2y subtract 4 is greater than 6. We want to find all numbers here that work in this inequality. So first, we want to get y by itself by taking the -4 and adding 4 to both sides. So that'll give us 2y is greater than 10. And to solve for y, we'll divide both sides by 2. Y will be all numbers greater than 5. And you can also check these just like equations. If you take numbers greater than 5 and plug them back in here, it'll make perfect sense. You might end up with like 10 is greater than 6 if you take a number greater than 5, or 15 is greater than 6, or 1,000 is greater than 6. See, so unlike equations, when we solve inequalities, we can have infinitely many solutions to this problem. Whereas when we solved equations, we usually just had one answer that was the only answer that worked. So on this one, Greater than 5 does not include 5. We'll put the open circle, and we will shade all numbers greater than 5, including the arrow. And why is the arrow important? Because these things go on to infinity and beyond. Yeah. Okay, so a little bit of graphing here going. All right, now let's go back to the graphic here next. And this is very important here. This is a huge rule with inequalities that I see a lot of students make mistakes on. Whenever you multiply or divide an inequality by a negative number, flip the inequality. All right, so in other words, change greater than to less than up here, or change less than or equal to greater than or equal, and so on. And notice the caution I have down here, and this is a big caution. If you don't flip when you need to flip, your grade will be flipped. And that could be from A to F. So be very careful on this point here. All right, now let's look at this and we'll see why. Let's go back to some examples here. So notice I've got the huge red caution flag out. Whenever you multiply or divide an inequality by a negative number, flip. Why, Young? I mean, some students will say why, and a lot of people say, well, the instructor said so, that's why, you got to do it. No, that's not why, and I'll show you why it's not why. I'm going to give y'all an inequality here that I think everyone will agree with. 10 is greater than 4. 10, 4 backdoor. I think we all agree with that. All right? Now, if I go adding 2 to both sides of this inequality, is it still true? Why, certainly. 12 is greater than 6. It is still true, and by the way, this is called the addition property of inequalities. So there's properties for these as well. If I take that 10 is greater than 4, and I subtract 2 from both sides, is it still true? Well, we get 8 is greater than 2. Yes, it's still true. So it appears that if I have a true inequality, adding and subtracting does not affect it. It still makes it true. Let's stay with that thought. Let's multiply both sides of this true inequality by 2. Still true? Yes, because we get 20 is greater than 8. All right, so it appears that multiplication does not affect this creature. If I have 10 is greater than 4 and I divide 2 by both sides, I still get a true statement. 5 is greater than 2. But watch what happens when I take Mr. True Inequality here and I go multiplying or dividing this by a negative number. We end up with negative 20 greater than negative 8? No. So that's why whenever you multiply something that starts out being true by a negative, or multiplying or dividing by a negative, you must change that inequality. So in this case, it went from greater to less. That is a huge point. Be very careful there. And it's not because some instructor said it's a rule, because it makes sense when you use numbers on it. All right, so big point there. So I think it's a good time to stop and run through some study tips. All right, because we always like to incorporate study tips when we are doing the show here. So let's talk about study tip 1. We're going to kind of keep going through these as we go on with the series. And step 1 is that get organized. A lot of students I've seen in my career who have struggled with math, they're never organized. They have papers everywhere, stuffed in their textbooks, on the back of napkins, you name it. Create a math folder and keep it organized from topic to topic. And review notes and examples, this is number 2, the day they were taken. This will reinforce each concept and solidify it in your mind. Okay. Now, here's what I get in my office sometimes when students come in with notebooks. They say, Mr. Young, I need help. I'm trying to find the problem here, and they're sitting there going through things, and they can't even, they're not organized at all, and this is very difficult. I mean, I even get dinner napkins sometimes and stuff like, oh, I have a problem on here, and I mean, that's not the way you want to try to do things in math. You can't have a notebook or textbook stuff full of papers. You're not going to get anywhere. It's just not going to work. So Young is building, as we go on, the empowering Introductory Algebra notebook. A notebook where you have things, papers you can take out on one side. It's organized from topic to topic. And we can go down here on the examples and show this notebook here. So it's a notebook with pockets you can take things out of. It's got topics in here. And the thing you have to do is when you get done getting these topics, work problems. Make that effort. It's time well spent. desire to succeed. These are things instructors can't teach you, but if you go through topic for topic, keep things organized as we go through here, you're going to be very successful. You're going to be very successful. All right, let's get back now to some inequalities. And let's go back to some examples of solving. And I just wanted to see if you guys can remember a few things here, this inequality versus this one. So on the left, to solve for x, we're going to divide both sides by a positive 3. Do we flip? No, we didn't multiply or divide by a negative, so the answer is x is greater than negative 3. Versus over here to solve for x, this is negative 4 times x is less than or equal to negative 12. We would have to divide both sides by negative 4. And when we divide by a negative, boy, you should have those sirens going off in your heads. Flip that inequality and watch your signs here. Negative divided by negative, x is greater than or equal to 3. So a huge difference between multiplying or dividing by a positive number versus that negative number. Yeah. All right, more difficult examples, you ask? Why, certainly, we just don't do the easy ones on this network. So multiplying through here, we've got some distributive property going from the past. So 6 distributed through gives us 12x minus 24 plus 8 is greater than, multiplying the negative 3 through here, negative 3x plus 3 minus 7. All right, so now collecting like terms, we're going to have 12x, negative 24 plus 8 comes out a negative 16 is greater than negative 3x, and then combining the like term numbers here, plus 3 minus 7 gives us a negative 4 or minus 4 there. Okay, letters on the left, we'll go ahead and bring the negative 3x's over by adding 3x to both sides. So that will give us 15x minus 16 is greater than negative 4. So notice I've done nothing thus far to have to change the direction of the inequality. Okay, so I'll put the letters left like I did on previous lessons to show I'm taking the letters to the left. And then the numbers I'm going to take to the right, and I put the old NR on those by adding 16. So again, when we're adding and subtracting, this direction does not change. We get 15x is greater than 12. Okay. So now to solve for x, to take out the multiplication, we're going to divide both sides by 15. So x would be greater than 12/15. Now, does that fraction reduce? I think so. I think there is a number, and you always want to look to reduce fractions when you're doing these problems. So what number goes into 12 and 15? That would be 3. So always reduce fractions on any problems to lowest term. So we would end up with x is greater than 4/5. And yes, you could even graph this on the number line if you had to. 4/5 is between 0 and 1, a little closer to 1. Open circle, shade it to the right. All right, so in closing, remember the successful strategies we are trying to instill in each of you. With effort comes understanding. With understanding comes success. And with success comes confidence and perhaps even happiness. Think about it, take care, and we'll see you next time.